Good afternoon, everyone. This is the afternoon session featuring a young MFEM scientist. The format is, we have two student sessions. The first one has 3 talks. Each will be 10 minutes, and we'll hold the question Q&A, after the end. So we'll have the 3 talks, then 15-20 minutes for Q&A. Then we'll do the next 4 talks, again, 10 minutes each, followed by Q&A. So with that, we'll let Julian kick off this session. Julian, we see your screen.
Hello, can you see me too? Doesn't matter if you don't, but just wondering.
We do.
Oh, all right, great. So hello, everyone. So today I will talk a little bit about atom probe tomography, or APT, which is a method used for material analysis, and how we use MFEM to help understand some of the things that happen in APT. But first, a tiny little bit of context. So the semiconductor industry pushes the limits of transistor density, and these components are already so tiny that we need to control the location of atoms at the nanometer scale. The design is moving from conventional 2D structures to increasingly complex 3D structures. And apart from the process technology, we also need to have the proper characterization to evaluate if the atoms are where they should be. This is where atom probe tomography, or APT, comes in, as it is the only method that combines nanometric spatial resolution and elemental sensitivity in 3D. However, there's an unresolved problem APT users struggle with. Have a look at this image where a non-planar transistor was analyzed. When compared to a TEM image of the same sample, we can see spatial distortion. To understand what is happening, let's have a brief look at how APT works. APT is based on the evaporation of a needle-shaped specimen using an electric field and a laser. The resulting ions follow trajectories determined by the electric field and are identified at the detector. To reconstruct the original specimen, each ion impact position at the detector is mapped to the location where it left the specimen. And to simplify things for this reconstruction, the current industry standard assumes a hemispherical needle tip at all times. This results in a relatively simple model of the ion trajectories, but in reality, the shape is affected by different material species having different evaporation probabilities, and the laser effect is not necessarily uniform, thus resulting in all kinds of tip shapes, which has a significant effect on the electric field, resulting in the ion trajectories being different than initially assumed. This explains why the shape assumption fails and produces error. This is why our aim is to develop an accurate reconstruction model, and to do this, we want to follow these 2 steps. Step 1 is the development of an accurate simulation model of evaporation, and the forward operator developed in step 1 will be used in step 2 to inform a reconstruction model. And the forward operator we developed is called ADAPTS. It's the Adaptive Atom Probe Tomography Simulation Library. It's currently still a work in progress. And on the right-hand side, you can see one of these specimens, like a very tiny one, evaporating with the field magnitude plotted onto each single atom here. And you can see these terraces of atoms evaporating starting from their edges. And then you can see like trajectories originating from these evaporation sites. And these trajectories end up at the detector, and this forms a heat map. So on the left side, we can see this density map. This is just the density of the ion impacts, which resembles features of the original specimen. So this is what we are essentially interested in ultimately, going from this left side to a specimen as we can see it here on the right side. So the general procedure of this forward simulator goes as follows. First, we need to generate a mesh which models the specimen and the vacuum chamber. We use MFEM to calculate the electric field on the whole domain in the next step, and then we select the atom that is most likely to evaporate, and then we integrate the trajectory using Newtonian motion equations. And essentially, we just repeat this procedure until we fully evaporated our specimen. Now, one thing about APT is that the specimen is very tiny. The length scale of the whole thing is like tens of nanometers, but the vacuum through which the evaporated ions travel is quite large in comparison. The length scale here is tens of centimeters. So this is 8 orders of magnitude in difference. So when generating a mesh in ADAPTS, we first place vertices in our domain and then perform a tetrahedralization. So this is like a different way of generating meshes. And each atom locus in this mesh in the specimen is represented by one mesh vertex, and this way we can capture the geometric protrusion of single atoms due to the terraces that we can see here. And for the vacuum vertices, we use a different generation strategy. So here we use something called tree-based variable density Poisson disk sampling to essentially capture still the shape of the specimen in the vacuum that is very close, in the part of the vacuum that is very close to the specimen. But as we go further and further away, we want this resolution of the mesh to rapidly decrease. And so we use this tree-based variable density Poisson disk sampling. That's a mouthful. And this method works by enforcing a minimum distance criterion between the vertices. And this minimum distance is a scalar field, which depends on a level set function of the specimen shape. So currently, I just implemented this for implicit shapes, where I can just directly specify the level set function. But I'm currently working on getting it working for surface meshes as initial specimen shape as well. So in this figure, you can see here on the left side this level set function. Then this gives rise to this vertex sample you can see here in the center. And then on the right side, we can see just the triangulation of this, and we perform this triangulation. Well, this is just a 2D example. In reality, we do this volumetrically for a tetrahedral mesh, so it will be a Delaunay tetrahedralization, and for this we use TETGen. Yes, and in specimens with 10 million atoms, we find that even though the vacuum represents almost all of the space, it is only represented by 2% of the vertices in the mesh, and the other 98% of vertices represent the actual atoms. And this is good news because we create almost no computational overhead for the vacuum itself when calculating the potential and field. The images, that you just saw, they are 2D. Now the actual mesh is tetrahedral and looks something like this. And in this image, you can see a 3D mesh generating using this procedure. And the specimen here consists of two kinds of atomic species, the magenta and the orange atomic species, and the vacuum in the background is represented in blue. And ADAPTS now uses MFEM to solve the Poisson equation to acquire a solution for the electrostatic potential. And this is very similar to how the Volta mini app works. We just have this H1 finite element space, and we apply Dirichlet boundary condition at the base of the specimen. Then we use the diffusion integrator and solve using PCG. And now by taking the negative gradient of the electric potential, we acquire the electric field. And because we want to know the electric field at the vertex locations, which represent our atoms, we use the same finite element space and derivative integrators for x, y, and z directions, and then again solve using PCG. And now when you look at the figure, you can see that the most protruded atoms have a larger electric field, which is realistic, and the highest field we find at the intersection of the surface and the material interface, which, if we remember, it was like a circle on the surface essentially, and we can see that this circle, it's a little bit brighter than the rest of it. And then on the background, we can see just the electric potential because the field is here almost zero everywhere. So like in comparison, it's relatively small, but it's not negligible. So that's the problem here. So using the electric field solution, we select the atom that is most likely to be evaporated. And currently, this is just performed using the atom with the highest field. Bear in mind that this is still a work in progress. And then the integration of the trajectory is performed using just a forward Euler scheme. And the field at some location is just assumed to be always the nearest neighbor. And the time steps now scale with the level set function used in the variable density Poisson disk sampling. And now the trajectories are terminated upon intersection with the detector plane, which then yields our heat map. We now covered in short all of the steps performed in this diagram, but to accelerate things, we can use submeshes in the following iterations. And this we can do because the evaporation changes the electric field, but this change only occurs close to the evaporation sites. So to accelerate our simulation, we can generate a submesh using a neighborhood of the evaporated atom, transfer the potential from the last iteration from the parent mesh onto a submesh, tag the boundary of the submesh as Dirichlet, solve the electric potential on the submesh, and transfer the submesh potential back onto the parent mesh, which is where we then solve the electric field. I'm not sure if this is the fastest way to do it. I don't really believe so myself, but it's really fast still. So calculating the potential takes much longer than doing the derivative integration. When compared to the other tool capable of simulating atom probe, we find that ADAPTS is significantly faster. And although we can see on the SID map comparison a few differences, so it doesn't look the same. The major features, so these so-called zones, these are these zones right here, and the poles and zone lines, they are essentially the same. But keep in mind that neither of these models has been experimentally validated in a quantitative manner yet, so take it with a grain of salt. It is also not clear how accurate the simulation has to be to provide a good reconstruction, which is where we are ultimately headed. Because, that I didn't do yet. Anyway, thank you for your attention.
Hello, everyone. Today I will be presenting the work I did with Ketan during the summer in attempting to port the routines that exist for find points for volume elements to surface elements. And I just say, and of course, this given the understanding that surface elements go from a three-dimensional physical space to a two-dimensional reference space, and that doesn't provide us with information in the normal direction that we would need to describe the bounding boxes in the normal direction of the element. And so, given that restriction, let us first define what we mean by searching for a point in a space. What we mean by that is given the idea that we have a physical space and the physical space is described as a transformation of a reference element. So if a reference element, let's say, goes from -1 to 1 in the 3 or 2 dimensions, we define a reference coordinate r s t. In our case, it will be just r and s, and that will map to a three-dimensional space and the space belonging to a three-dimensional element. And so when we say search, what we mean by that is we want to know which rank does the point belong to, and we want to know which element the point belongs to, and we want to know what the reference coordinate of that point is inside that element. And so this has been covered by Ketan already, but I will just give a brief overview because it in the context of the surface, the changes in surface meshing. What we want is to rapidly identify which rank the point belongs to, and then in that rank we want to rapidly identify what are the candidate elements that may contain the point. And once we have the smallest possible set of candidate elements, we want to then do our Newton search or some kind of Newton minimization method. So the goal is to do the first step, the first two stages, which are essentially a one-time cost if the mesh is not changing, as fast as possible. And for that, what we do is we use
Yes. Secret.
What's the system? It's
Okay, is it the system? Can the other people online hear us? Yeah, we can hear you online.
I think Adi, you're back now.
oh, okay.
Last
Oh, yeah, my internet connection. Where did I lose you guys?
this slide, it was the beginning of the next slide.
Oh, okay. Yeah, so essentially to do this fast, what we have to do is we have to use Cartesian meshes which are uniform and essentially can be described using a mathematical formula because we have a minimum extent and a maximum extent and a number of elements. And what we try to find out is, first of all, what are the ranks that contribute to a particular cell of the Cartesian mesh in the global sense, and then what are the elements that contribute to a particular cell of the local Cartesian mesh. To find that out, we want to know the intersection of the elements with the cell, and that is not trivial. And so what we do is we end up creating a bounding boxes for the elements which are linear and for which the intersection process is very trivial. So that brings us to the first type of bounding boxes that we would deal with is axis aligned bounding boxes, and the calculation is not that straightforward for higher order elements which can curve and which not necessarily have the maximum or minimas at their nodal values. So what we have to do is we have to convert them to piecewise linear functions, have some piecewise linear bounding functions, and then bound them. And what we can see is this yellow bounding box shows essentially how it deals with curved elements. One interesting result of dealing with surface meshes is that elements that are perfectly aligned, like these linear elements that are perfectly aligned with the axis, end up having zero extent in one of the dimensions, which is not good for us because we want to have some notion of distance in that direction. So we have to add some tolerance in that direction manually when it's perfectly aligned. The other kind of bounding boxes are oriented bounding boxes, which end up reducing the amount of volume that element represents significantly, and thus allows us to weed out more points from more elements from being candidate elements. What is the time? Oh, okay. So essentially, they provide a stricter check for us. So as you can see from here, the difference in the volume that's occupied by access line bounding box versus a oriented bounding box. The process of evaluating oriented bounding boxes is slightly trickier in the surface mesh case because we don't have a clean transformation from we don't have a transformation that captures the three directions, the normal direction to the element. So what we have to do is we have to essentially generate the transformation matrix ourselves. And what we do is we first move the element, the center of the element to the origin of the domain, and then we rotate it so that it's oriented, its tangent is oriented along the axis, and that allows, and then we draw axis line bounding box on that rotated element, and which is essentially the oriented bounding box for that element. And then we scale its lengths so that it goes from -1 to 1. And this box, so if we multiply these transformations through the process, we can then go directly from the physical space to the to a space of -1 to 1. And that allows us to find out whether a point is inside the oriented bounding box or not. For the 3D case, the idea is similar. It's just that now we have information of two tangents at the r, comma s equal to 0, comma 0 location. So we calculate a normal direction, then we orient the normal direction so that it's along the z-axis. And that at that stage, we calculate the z bounds because the physical dimensions of the element is still the same. Then what we do is we project the element on the xy axis. And that is, we just consider the xy coordinates of the element once it has been rotated. And then we calculate the Jacobian of that rotated, projected set of coordinates. That we can do by just transforming the original tangents by the same rotation. And once we have done that, then we create a bounding box. We scale it to a different size. And then all the transformations, when applied to the original physical space, gives us information of if the point is within the bounding box or not. And so I tested it with quite a few meshes, but here just two examples. One is the star mesh and another is the Klein bottle case. And from left to right, we have just the original input surface mesh, the global hash mesh. I have not shown the local hash mesh here. And then the axis line bounding boxes and the oriented bounding boxes. And we tested the interpolation accuracies, and all of them are essentially machine precision. We have tested them with around 10 to 100 million points as well. And oh, it's almost there. So, well, I'll skip this step because I think we have heard this from Ketan too. But this is thanks to Ketan. He also did some performance tests for the surface implementation. And what we see is that around 10 million points are evaluated at around 10 power minus 1 seconds. And this is the case for, this is the interface for the triple point. mesh. And so thank you.
Hi everyone, I'm Gabriel Pinochet-Soto, fourth year PhD student at Portland State University. And today I'm going to talk briefly about my work during my internship at Lawrence Livermore. It was a joint work with Sania and Jack, and it was basically mainly based on preconditioners of diagonal preconditioners and smoothers in MFEM. And well, our main goal was to develop a generalized kind of Jacobi preconditioners so we could use multi-grid methods and check their convergence and their utility in MFEM. And at some point, we also make a step forward, and we're also trying to precondition systems that are partially assembled, and that's something I'll mention later out in the talk. So some preliminaries. For simplicity, and because I'm going to talk about multi-grid methods, multi-level methods, I'm going to consider a system that comes that yields a symmetric positive definite operator A. I'm going to recall that on smoother, it's A convergent if the following matrix M plus M transpose minus A, it's a symmetric positive definite. This implies that the error propagation matrix of the method has norm strictly less than 1 in the A norm. Something also that's relevant for the preconditioners we will define later on is that the off-diagonal entries of the operator A are bounded by the diagonal entries, and this is just a Cauchy-Schwarz inequality that yields this inequality. And I also want to recall that at some point we are testing a lot of different preconditioners, and we would like to see different smoothers in the context of a two-level method. We would like to see if they are convergent or not. And that convergence, it's related again to this term, M plus M transpose minus A. So the two-level preconditioner matrix, it's going to be a symmetric positive definite if M, the smoother, it's A convergent. So we have Sania had this idea of trying to precondition systems with generalization of Jacobi preconditioner. We know that, and I'll show you later in a second, that L1 Jacobi smoothers are nice. They are simple to compute. They are convergent. They yield good results, and they are diagonal, so it's easy to apply. So the main idea is to generalize them to a family of preconditioners and see if these preconditioners yield similar properties. So what we're doing here is taking the diagonal elements of our matrix and reweighting them with some sort of P norm, and the off-diagonal entries are going to also be reweighted in terms of the diagonal entries, in terms of given by these coefficients. We don't know this. We don't know a priori if these preconditioners and these matrices will be convergent or not. But that's something we are aiming to describe to some extent and see if it yields a good result or not. One of the main works I did during the summer was to implement this formula. This is again here in this summarized compact form, where the operations we're doing in here are given entry-wise. The absolute value of the matrix, it's taken entry-wise. The P and Q powers are being taken entry-wise. So this is even if it's not as cheap as L1, for instance, it generalizes the ways we can compute these preconditioners, and it's let's say simple to implement. You take a constant vector, you rescale it by the diagonal, you apply the absolute value of the operator to a certain power, and then you rescale it again by the diagonal. That yields a vector that provides us a nice matrix. Why this formula? It's mainly based on modifying the exponent that we would use in the case of L1 Jacobi, and these weights are based on that Cauchy-Schwarz inequality I showed you early on. Some examples, if we assume temporarily that the matrix is diagonally dominant, we can deduce some cases where this matrix it's easy to recognize. For instance, if we set p equals 0, we get a row-wise rescaled Jacobi smoother. That means you take the diagonal and take the number of non-zeros per row. If you set p equal 1, we obtain the L1 Jacobi smoother. If you set p equal 2, you get a matrix that's an argmin of solves a minimization problem. And if you take p equal infinity, if you let p goes to infinity, we recover the traditional Jacobi smoother. So these operators, these matrices are they are comparable in the spectral sense. Whenever in some sense they are monotone with respect to p and specific q's, and well, we can prove that they are convergent for some p's because we just mimic the proof we have for L1 Jacobi. A weighted Jones inequality yields that the L1 it's convergent. So we have a full family of convergent smoothers, but we wonder if increasing this value of p will make it better or not. I'll show you some results later. So now I'll go into another problem we had also and interesting. Sometimes we don't have this full matrix assembled. We only have the partial operators that define the structure of the operator, the big matrix we have. I recall, I think Sani or Veselin already mentioned this briefly. So now that we have A as a product of operators, we would like to precondition this. As we don't have access to each entry of the operator, one idea to implement an upper bound for a spectral upper bound of the L1 Jacobi is to take absolute values of all of the entries of these operators and generate this new matrix that also yields a convergent smoother and test its behavior and see how good it preconditions some systems. So my task was to implement these two things. Notice that the scope, it's quite different. In one sense, I'm handling hyperpar matrices, so it's easier to modify this. In here, I need to precondition B transpose DB, and that implies going to the integrator level and handling those cases. So here I have one simple example, diffusion problem, grad integrator on the ICF mesh. That's pure. It has tensor elements. We see that for different values of P, we get a good smoother for multigrid. At some point, it stops working because, as I showed you in the first slide, the iteration matrix may fail to be positive definite. That's the main issue. But it works pretty nice. We can do order refinement on the ICF mesh, and the smoothers work fine. In particular, we also check that we do have a preconditioner for a partially assembled case that actually does cut off the number of the number of iterations we require to solve the problem with CE in this case, with conjugate gradient. That's mainly it. Do I have more time?
Well, yeah, maybe, yeah.
Okay, so I'm gonna show you some extra slides. So let me first summarize some things and then go into slightly more details. This work, it's already into a PR. It's getting reviewed. It's almost available for being used. And it consists on a mini app. So the first part of the work was focused on implementing app small. power apps mode for hyperparametrices. It's something that I did in the first half of my internship. And then the second step was to implement this absolute value application of the integrators, and that require modify and take a look at some kernel functions. So as I said, it's a mini app now that wraps some multi-grid examples. You can compare it with example 26, and you can also compare it with examples 1, 2, and 3, because it also includes mass integrator, chord curl, vector mass integrator as well, and diffusion, and elasticity.